Example for class 8. There's a lot of examples, but man, that's good. It's a good thing to have examples, but I would really highly encourage you to try to work through them yourself without peeking at this video, and because they all end up being pretty. Everything looks easy in the rear view mirror, right? So it's much more difficult when you looking at a blank sheet of paper and having to start yourself. So here's another problem. I think this is out of juvenile. I should look up and give the attribution for what problem number this is. So we have this quarter-inch diameter ball. It's being pressed up against the ends with 1,000 pounds force of this shaft thing, and against the left end of the bar, it has a cross section of 1 inch by 1 inch, I guess is what they're saying right there. So I guess that's what this guy right here. The balls are hardened steel, and the steel bar has a yield strength of 50 ksi. What maximum contact stress will result from the load of 1,000 pounds? And I think there's a couple things in here that are supposed to throw you off, like the cross section of the bar being 1.5 inches in one spot, and being an inch at inch and a half right here, and these lengths and that type of thing. Maybe this is part of another problem where they ask other things, so they ask something from the same figure. I don't know. I'm going to go look it up and find out what they were doing. But I think there's a lot of stuff in there that you don't really need. Right? So let's take a look at this problem if we can get the thing to focus. Okay. So this is a contact stress problem, and similar to one I did in class. This is really a sphere against a flat surface. So proceeding in with some of the things we want to know, we say the 1,000 pounds. I went ahead and said the steel was elastic modulus of 30 e to the 6 psi, right? So 30 million psi. And this time I used a Poisson's ratio of 0.3 because that's what's in the table right there. I don't think they didn't tell us anything more in there, so that's a good estimate. The diameter of one of the things is 0.25 inches, and the diameter of the other thing is infinity. It's just flat, right? It doesn't have a diameter. So I go ahead and I use my equation for the radius of the interface between, right? This is 1/2 of the diameter, and the equation is 3f over 8, and then these are both the same material, so I'm going to just put a 2 there and say 1 minus nu squared divided by e. Otherwise there would be a separate one for each of them if they were different materials. And then we have 1 over d1 plus 1 over d2, but d2, remember, is infinity, so that one just goes to 0. So we have 3 times 1,000 divided by 8 to 1 minus 0.3 squared divided by 30e6 divided by 1 divided by, and this should be in inches, yep it is, 0.25. And we end up with 0.01785 inches. And now if we want to go to the P max, this is the maximum pressure we're predicting, is 3 times F divided by 2 pi A squared. Or 3 times 1,000 divided by 2 pi, and then the answer we just got. And we get 1,498.5 KSI? Sure. Wow. That's a lot. And if we go ahead and look up in the book from the contact, and I'll go ahead and grab it. We go to the contact stress right here, And we look up here is the sphere versus sphere, but of course one of our spheres is a flat plate. We will look and we say that's 0.3 times P max, right? So all we have to do is multiply that by 3, and we get the tau max, the maximum shear. That's going to be the 0.3, and so P max that's happening onto this thing is 0.3 times 1,400. There, see what I did? I just cheated. 499, and we get 449.6 KSI. So tau max is equal to 450 KSI, and they told us that the yield strength was 50 KSI. Did they say the yield strength? Well, they say the yield strength is 50 KSI. So what you might come to a conclusion is that thing is leaving a dent. That's what that really means. But how much of a dent? Would you even be able to tell the size of the dent? Now, this is like once it's gone beyond the yield strength of something, it doesn't act linearly, right? But we're predicting a linear type of thing right in here, right in this is like a linear displacement. That, well, maybe it's not exactly linear, but it is going to predict. We're predicting the displacement in small amounts, right? So the larger dent that it might make onto the thing. I don't know if I can make that overall assessment onto the thing. Let me just back up and say that there's a good chance it's going to leave a dent. But we also quite often will have like surface hardened pieces of equipment that will be able to withstand. So there'll actually be some strength. It'll actually be harder and stronger right there at the surface as opposed to the nice chewy, gooey, delicious nougat center that you have in your bar. So it might be able to withstand this. Maybe that for the application they've done some surface hardening to be able to withstand that. Or maybe it just said, there might be really high stress, but it's really local, right? It's a very local thing, and it might leave a little dent, but it might be such a small dent that'd be imperceptible, or it might not matter. Maybe they just don't care. Maybe their whole purpose of this thing is to leave dents in the end of this. I don't know, but we have an estimate of what that maximum shear is. Remember, it's below the surface. So it was another example, and I feel as though that this is a good amount of examples for a refresher to see where we've been. Sure. Enough talking.